Hey all, and welcome to our next week of talking about some counting principles. Last week we talked about permutations, and if you remember from earlier years, that means that combinations can't be far behind. So get yourself ready for notes, and we're going to get started. Now, combinations are a way to count different arrangements where order doesn't matter. So we talk about this as n choose k. You'll see both notations. This is maybe how you're more familiar. This is how you'd enter it in on your calculator. It's also written like this, where it kind of looks like parentheses of a small matrix that's just 2 by 1. And it's the same as n factorial over n minus k factorial times k factorial. And again, it's n choose k, the number of ways to select k elements from n total. The big difference here is that order doesn't matter. That having 1 and 2 be your selection is the same as having 2 and 1. So that's why we have this additional divided by k factorial from permutations to divide away all the ones that are the same set but in different orders. So the first thing that we're going to talk about is calculating these without a calculator. If you do have a calculator, you can obviously enter it in like this. Here we have 13 choose 9 without a calculator, which means that 13 is our n value and 9 is our k. So when we plug that into the formula, we end up with 13 factorial over 13 minus 9 factorial times 9 factorial. This is going to simplify to 13 factorial over 4 factorial times 9 factorial. And the nice thing is, if you want to write out that whole expanded 13 factorial, I'm going to skip a couple numbers in between, but we've got 13, 12, 11, 10, 9, and all the way down to 1 and 2. And what nice thing's going to always happen with combinations is that you have your 9 factorial here, and then 4, 3, 2, 1. And what you'll notice is that there's this same number of numbers in the numerator and the denominator. If that's not true, you did something weird. The other thing that's always going to be true is that things will always simplify completely. So 4 times 3 cancels out with the 12. 2 times 1 cancels out with the 10. Leaves behind a 5. And so you're always going to end up with just integer multiplication. So 13 times 11 times 5 in this case. Again, if things don't simplify that nicely, you've done something wrong, because you should always get an integer answer for both combinations and permutations. So how do we use combinations? Well, if we look here for number 2, it says, how many ways can you choose 3 letters from the alphabet? So here we have choose, so we know we're going to use combinations. And we have 3, we're choosing 3 out of the alphabet, which tells us that our n is equal to 26, because there are 26 letters in our alphabet. So 26, choose 3, which is 26 factorial over 26 minus 3, so 23 factorial and 3 factorial. Now one thing is I will start just canceling out, so like 26 factorial over 23 factorial leaves behind the 26, the 25, the 24 in the numerator. The rest cancel out, and then we get 3 factorial in the denominator. So I'll often skip that step just to make my life a little bit easier. 3 and 2 and 1 is 6, cancels out with the 24, which leaves us with 4. So again, we know we're on the right track because we have just simple integer notation here. Some might want to grab a calculator. Oh no, 26 times 25. Well, you can also just do 25 times 4, which is 100, so then we have 2600 as our final answer. This is also, you'll notice the title in both the objective here, counting subsets, and in your textbook reader is going to have to do with subsets. So in this case, we have a good fact about combinations is that we have a question, how many 4-element subsets exist from the set of the digits? And here's a helpful fact is given the cardinality of A is equal to n, then if you have a subset of A with cardinality k, meaning a subset of A with k elements, the number of those subsets is equal to n choose k. Now, this is helpful in a lot of ways, and I'm just going to write this again in a way that will hopefully be especially clear, is that the idea is that if A is equal, if A has n elements, there exist n choose k subsets of A with k elements. This is also an important thing to note, is that if k, let's say, for example, k is greater than n, so if you tried to put in something like 2 choose 17, it will let you do this. It's just always equal to 0, because logically there are no subsets with 17 elements if we started with 2. So we'll come up with an answer. It'll be 0. So in 3, it says how many subsets exist from the set of the digits? Well, the cardinality of this set is 10, so that's our n, and we have 4, and that's our k. So we can plug that directly into the formula of 10 factorial over 10 minus 4 factorial times 4 factorial, which is 10 times 9 times 8 times 7. The 6 factorial down here is canceling out over here. And over 4 times 3 times 2 times 1. Simplifying, the 4 and the 2 together cancel out the 8 entirely. The 9 and the 3 simplify, and we get 10 times 3 times 7, which is 210. We might answer a more complicated question. 4, how many 4-element subsets exist from the set of the digits that have 2 odd numbers and 2 even numbers? So if we have 2 different constraints here, we can think about them separately as choose 2 odd numbers. So we're choosing 2 out of the 5 odd digits, 1, 3, 5, 7, and 9, and choosing 2 even digits from the 5 even. To find the chance of both happening, we're going to use the multiplication principle, and this will tell us this is then the number where both are happening. So multiply these together. They both end up being 5 times 4 over 2 times 1, and then I'm just going to square that since they are identical, which gives us 20 over 2, which is 10 squared, which is 100. There are 100 subsets like this. I also want to make sure that we are practicing with these higher level of thinking problems. So for this case, we see find, it says the cardinality of x is an element of the power set of the digits where x is less than or equal to 2. This is a very complicated looking statement. So the first thing that we'll do is translate it. Find how many x out of p. Remember, this power set is the number of subsets, so it's asking find how many subsets of the digits have less than or equal to 2 elements. So the way that I would think about this is I would ask, well, how many have 2? And then less than would be 1, and less than that would be 0. Some of these are going to be easy. There's only one subset that has 0 elements. That's our old friend, the null set. So some of them you don't even have to do calculations there. Another one, if you wanted to do 10 choose 1, you could, but also how many are there with 1 element? Well, there's 1, 2, 3, 4, 5, 1 for each element of the set. So sometimes you could do the, in this case, 10 choose 2, because I don't want to do quite that math off the top of my head, but some you can just write them in. 10 choose 2 ends up being 10 times 9 over 2, which is 45, plus 10 plus 1. Since it's less than or equal to, we add them all up, and you end up with 56 as our subset. We're going to start seeing more and more algebraic proofs. So in this case, you're going to see a lot of proofs with combinations. This is going to be true for the next several months. So we're going to start with some straightforward ones in this homework set. And this is when you're going to start really using that additional workday on Thursday. So work on the proofs. Make sure you feel confident that you can create them on your own. If you have questions about them, please don't hesitate to set up a Zoom call or leave me anything in the comments. So prove that n choose 1 is equal to n choose n minus 1. So what I always recommend with these types of proofs is start with the less simplified one, the one with more terms, because then that means you have more to work with. So when I say start with that, I mean take that side, and we want to algebraically manipulate it so that it equals this side. It equals the thing we want. So sometimes I even recommend, well, algebraically, we know the thing we want is n choose 1, which is the same as n factorial over n minus 1 factorial times 1 factorial. This is our goal. This is what we're aiming for. So we're going to start off with our more complex one, and we have n factorial in the numerator over n minus 1 factorial times n minus 1 factorial. Now we'll do our algebra. Notice that we're only working from one side. This is also true last time that we did proofs. You're only manipulating one side at a time. You can't cancel things over and cross them out, because that would imply that we knew it was an equation to start with. So for example, we know these two are equal. We don't know yet that these two are. So we can't treat it like an equation yet. So now we've distributed the negative in the parentheses, so we get n minus n plus 1. N minus n cancels out. So we are left with n factorial over 1 factorial times n minus 1 factorial. And this is why it's nice to know, oh, what we want, we're nearly there. We just are going to commute. We're going to move the terms like the commutative property in the denominator. And now we say, oh, well, that's actually equal to n choose 1. We finished our proof. And by the transitive property, this side here is equal to this side over here, and that's exactly what we wanted. So here's one of our first algebraic proofs. You've got some in the homework, so make sure that you're working on those as well. I'll talk to you later.